Hello, my name is Jim Freerichs, and today I'm going to give you a talk on describing how we can pivot the undergraduate quantum mechanics class to support training in quantum sensing. This is work that's been funded by the National Science Foundation and by Georgetown University. But before we get started, as I'm recording this video, there are very serious events taking place in Ukraine, and I would like to have a moment of silence in solidarity with the citizens of Ukraine. Thank you. And now we'll get started. Quantum information science has three pillars. The first pillar is quantum computing. I'm depicting here an IBM quantum computer on the left and a typical gate-based circuit diagram for a quantum phase estimation algorithm on the right. The second pillar is quantum communication, and here I'm showing you a key distribution system and the famous BB84 communication protocol. And also quantum sensing. And for quantum sensing, I chose the global positioning system, which uses atomic clocks, and the Laser Interferometry Gravitational Wave Observatory, which is probably the most sensitive measuring instrument that mankind has ever made. Now, of these three pillars, physicists actually have the strongest overlap with the quantum sensing pillar. And I want to discuss how we can supercharge your quantum mechanics class for quantum sensing. Now, quantum sensing is a pretty big industry. If we include the global positioning system in it, it's projected to be a $130 billion industry by 2025. The rest of quantum sensing is growing, but is significantly smaller. This chart is showing forecasts that get up to about the $2.5 billion mark by 2028. The US government has predicted a huge need for a quantum-enabled workforce. And these are for people who will be working in industry, in academia, and in government. They have a number of different levels in which they describe what a quantum aware, a quantum proficient, and an expert are. And we're typically working with undergraduate physics majors. We're more in the quantum aware or quantum proficient levels. As you get into the PhD studies, then you'd be getting more into the expert levels. All right, so I don't think I have to tell you much about what doesn't work. What doesn't work is the way we actually teach quantum mechanics, which is using a differential equation-based approach. This has its origins in Oppenheimer's course from UC Berkeley, which got converted into a very influential textbook written by Schiff in 1949. And there was a similar very influential textbook that had its third edition come out in 1947 by Dirac. And essentially, these works were focused on quantum mechanics from 1930. There really was not that much more that was in them than the quantum mechanics that we already knew in 1930. A lot was known at that point in time. That's when Dirac wrote his first textbook. But it was focused for graduate students who knew a lot about differential equations. And since then, we've essentially taken that exact same differential equation approach, and we've carried it now down to the sophomore level in the physics curriculum. And the question is, does this really make sense, or should we be thinking about alternatives? I hope I will convince you by the end of this talk that we really should be thinking about alternatives to this approach. So how do you teach it otherwise? Well, the first thing is we need to do what physics education research tells us to do, which is to focus on conceptual ideas. And for quantum mechanics, there are 5 really important conceptual ideas: superposition, entanglement, complementarity, tagging, and measurement. Now, you might not be familiar with all of these, especially tagging might be a concept that you are unfamiliar with. In the way that I look at these different concepts, measurement is an irreversible change that you've made to the system, whereas tagging, which typically is used to create entanglement in your system, is a reversible process. And being able to distinguish between when you're doing a reversible change to a system versus an irreversible change to the system is actually a very important skill that we don't actually teach students very much in the standard curriculum. What are the resources for these conceptual ideas? Well, there are two incredibly good textbooks that tell you all about them. There's Feynman's QED textbook, and there's Daniel Steyer's The Strange World of Quantum Mechanics. Feynman's book focuses primarily on light, and Steyer's book focuses primarily on the Stern-Gerlach experiment. In my opinion, you should be covering both in a quantum mechanics class. And these ideas are actually very strongly influenced by Ed Taylor, who was one of the first people to try to use graphical visualizations to better explain the concepts that are in both of these textbooks. And this is a theme that I will emphasize as well. In fact, that comes in the next slide. Here I'm going to show you a classical Stern-Gerlach experiment where we send a current loop indicated by this arrow where the needle is pointing in the direction of the effective magnet that current loop represents as it goes through an inhomogeneous magnetic field and then hits against a screen. You can see as it goes through the field, it precesses, but it also gets pushed because it's an inhomogeneous field, and that push will make it hit on the screen at a particular location. And you repeat the experiment many times, and then you'll get a pattern. And for the classical case, it'll just be a straight line that is uniformly filled. Now, in the quantum case, we don't know exactly what the quantum particle is doing, so we illustrate it by a sphere. And here, instead of getting a continuous line, we get one of two results, because this is done with silver atoms. If we rotate the magnets in the Stern-Gerlach analyzer, here rotated by 90 degrees, and we repeat the measurement, again, we find that it hits the screen in one of two different places. And so no matter what the orientation is, the quantum result will always measure a splitting of exactly the same amount in these two different values, with the same splitting regardless of the orientation or the direction that we orient the magnet. And that's a very important fact from which you can then derive a lot of interesting quantum mechanical ideas, including things like the spin algebra. Now, the second thing is to get rid of the differential equation emphasis and instead use algebraic methods. As you probably have noted, if you teach a quantum mechanics course, students really like working with the simple harmonic oscillator using operator methods. Wouldn't it be great if we could solve all of the exactly solvable problems using those same kinds of methods? Well, it turns out you can. In fact, Schrödinger is the person who invented this in 1940. He extended this operator solution method to all exactly solvable problems and exactly solvable models in quantum mechanics. It also allows you to get eigenvalues without eigenfunctions, but you can also get wave functions algebraically as well. This is work that I've actually been involved in over the last couple of years, showing how you can generalize these algebraic techniques to also get wave functions. The third thing is to emphasize the experiments and not the mathematics. After all, we are physicists. We should be focusing on physics, and physics is an experimental science, so we should be focusing on experiments. Now, at Georgetown University, in a one-semester class, these are all the different experiments that we cover. And yes, this is a one-semester class, not a one-year class. And I'll just mention a few of these different experiments, ones that you might not be covering so much in your current quantum mechanics class. So we cover things like the Bell experiment, an Einstein-Podolsky-Rosen experiment, and the Hong-Ou-Mandel experiment. Of course, you've seen the Stern-Gerlach experiment, but we look at the delayed choice variants of the Stern-Gerlach experiment. We talk about atomic clocks, Rabi oscillations, the Hanbury-Brown and Twiss experiment. We look at the hyperfine charge radius of the proton. We discuss how deuterium was discovered. We discuss hyperfine structure and rotational molecular spectroscopy, and of course, single and two-slit diffraction. But we also talk about time of flight and E2E spectroscopy, which is a way that you can measure the wave function of the hydrogen atom in momentum space, nuclear magnetic resonance, high precision measurements, quantum key distributions, quantum seeing in the dark, how you detect single photons, and so forth. So there's a lot of experiments that you can talk about in your quantum mechanics class. Okay, I'm going to give you one example of this new way of teaching quantum mechanics by motivating how we get the canonical commutation relation via a focus on experiment. So the starting point is a postulate that quantum mechanics must be described through examining matrix elements of operators, and their time dependence is given by the difference of the energies of the states. This is essentially what Heisenberg postulated when he discovered matrix mechanics in 1925. And so we have 5 items that we have in the recipe for getting the canonical commutation relation. The first is that atoms have sharp spectral lines. The second is the Planck-Einstein relation, that the energy of a photon is given by h bar times its frequency. The next is the transition in atoms occur between stationary states. This is essentially the part of the Bohr model that you want to teach your students. Fourth is that the matrix elements will oscillate harmonically at a frequency given by their energy difference. In other words, what this says is that you can think of the atom as a dipole that is oscillating at exactly the frequency of the light that it's going to be emitting. And finally, we need to know that the total energy is the kinetic energy plus the potential energy. So here's how it goes. The derivation is due to Herbert Green. Derivation is in quotes because this is really more of a motivation than a rigorous derivation, although many of the steps that we give are rigorous. We start from the hypervirial theorem, which says take these 2 states, the initial state that the atom is in, which I'll call N, and the final state that it's in, which I'll call M, and evaluate the expectation value of the commutator of the position operator with the Hamiltonian. Now, you can just evaluate this because H acting on a state is given by its energy eigenvalue, and in this case, we'll get En minus Em by evaluating that commutator, and we're left with the expectation value of position. Now, using the Planck-Einstein relation, I can rewrite that as minus h bar omega mn, and then I have to use an important fact about harmonically varying functions. A harmonically varying function means it goes like e to the I omega mnt, and then its time derivative is I omega mn e to the I omega mnt. Now, if I plug that in, I can replace that omega mn in the expression above by the time derivative. So instead of measuring the q, I'm going to measure the time derivative of q, and I have to plug in an I so that it becomes I h bar times that time derivative. And then if I bring in the momentum operator and divide by the mass, I will then have the first half of this derivation, which tells me that this commutator, expectation value of the commutator between these 2 matrix elements is given by the expectation value of P over M with an IH bar coefficient. Okay, but now we just directly evaluate the commutator. Q, commutator with the kinetic energy, which is P squared over 2M, plus Q commutator with the potential energy, which is V of Q. Now, of course, Q commutes with V of Q, so we're going to get rid of that term. For the commutator with the P squared over 2M, we use the Leibniz rule for the commutator of a product. This is a very easy rule to derive, and you get that the P operator comes out to the left and to the right, and you're left with the commutator of Q with P in the center. Okay, so now if we assume that the commutator of Q with P is a number, I can collect those terms. Let me show you what they were again. We collect the 2 terms, and by collecting the 2 terms, by moving them to moving the P through, because we say that that's a number and it commutes with it, we then get twice as many of the terms. And now if you look at the 2 expressions in red, it's the same matrix element. So the numbers in front must be the same. That tells me the commutator with Q and P must be equal to IH bar. Another way of saying that is that if the commutator with Q and P is a number, then that number must be IH bar. Now notice how there was nothing that was really postulated in this motivation / derivation of this. It really was focused on using the experimental ideas and some of the simple ideas from early quantum mechanics in order to effectively derive this canonical commutation relation. So it is experimentally motivated, it doesn't need to be a postulate, and it for sure does not need you to talk at all about Poisson brackets or any of the other motivations that you find in most textbooks. All right, on to the main thing that I would really want to focus on. And I love this quote from Asher Perez in his quantum mechanics textbook. Asher tells us quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. So let's be sure to teach quantum science, not quantum science fiction. Now, who do we have to blame for this? None other than John von Neumann. John von Neumann created a theory for measurement, but as far as I can tell, it's pure science fiction. What he says is to measure a quantum observable, we first prepare the quantum state to be measured. We then entangle the state uniquely with the apparatus. Uniquely is important because we have to entangle the apparatus with each of the possible measured values so that the pointer states of the apparatus are correlated with the eigenstates of the measured operator. Sounds great. And then you either apply collapse at the moment of measurement, or if you're more sophisticated, you'll use decoherence theory because the pointer is a macroscopic object that'll fix the pointer position. Now, here's the problem. I mean, this sounds great. It sounds like a really well thought out, well motivated experimental procedure and theory to describe the experiment. But there's really one problem to this. I don't know a single quantum experiment that operates in this fashion. If you do, I would appreciate your telling me what experiment it is that actually operates in this John von Neumann paradigm. So why do we propose a measurement theory that really has no basis in reality? I'm not really sure, but I want to go back to Paul Dirac, who said, the only object in theoretical physics is to calculate results that can be compared to experiment. This is certainly a quote that many physicists take to heart. So we better be sure to understand what experiments are and how they work so that we can teach them to our students. So how do we actually measure quantum objects? In many cases, we infer the properties by clever experimental setups. Let's take a look at spectroscopy. This is probably one of the most important experiments that is done in physics and in chemistry. How is spectroscopy done? Well, we shine light in, we diffract it off of a grating, we measure an angle, and from that we determine an energy. So let's go back to John von Neumann. Where's the entanglement? I don't know. I don't think there's any entanglement. What is the pointer? Again, no idea. I don't see what the pointer is. Where's the wavefunction collapse? Now, there is a destructive event that occurs at the point in time where you detect the photon and you destroy it. But it's not really a wavefunction collapse. You've destroyed the particle. Spectroscopy falls into a wide class of quantum measurements that involve counting quantum particles. Such experiments don't actually obey the projective measurement paradigm given by von Neumann, and they're often not discussed in textbooks. So let's talk about some truths about photons. A photon is not just a particle of light. When you're teaching about photons in class, all you say it's a particle of light, or you say it's a particle of light that has an energy given by h bar omega, you're really doing a disservice to your students. You can teach them so much more about photons. And for sure, do not tell your students that it emerges when you take a laser and attenuate it, because a laser is never a single photon source of light. It is always a classical source of light. It is never a single photon source of light. What a photon is something that can be detected only once. Once you've detected a single photon, it's gone and cannot be detected again. It requires a special single photon source to create, not just dim light. And at the moment, although there's a lot of work being done to try to make on-demand single photon sources, at the moment, most single photon sources are what are called heralded single photon sources. Now, the first version of this that came out in the early 1980s was the calcium atom cascade source. And let me get the pointer. And this calcium cascade source, you use two laser lights to excite it to an excited state that is short-lived, and it has a twofold cascade. It first decays with a lower frequency light to this intermediate level, and then it decays to the second photon. The intermediate state is stable for about a nanosecond, so you know within about a nanosecond you're going to get a second photon coming out. That makes it a heralded source. So if I have my source of photons sitting here and have a focus of light, I can measure the heralded light, and then I can take the light that is coming out, the blue light, and I can send it down some tube to a detector. And the typical spectrum I'm going to get is something that I don't see anything until the time it takes the photon to travel from the source to the location of the detector. And then given the lifetime of that state, I have an exponential profile for the measurement of the photon. And when you actually measure this, and this was done by Alan Aspect, you get this beautiful picture with this nice exponential decay. Of course, you do get some dark counts here because no detector is perfect and there always are some dark counts, but you can measure the width of this, and this is what typically a single photon source will be giving you. Now, it's key that photons can be detected only once. If I put them on a beam splitter with 2 detectors, I can measure the number of times both detectors go off. I then put in here the number of times I've heralded a photon, so the number of times there's a photon in my apparatus, and then the number of times I get a single measurement in this detector or a single measurement in this detector. And what you find, this ratio is something called G2. And when this ratio is less than 1, then you have a single photon source, and it's equal to 0 for a perfect single photon source. If you did this experiment with a laser and made the lasers dim, and again, Alan Aspect has done this experiment with a laser diode, you find that the G2 is always bigger than 1. And indeed, it's important for students to be able to differentiate what is a true single photon source versus what is just dim classical light. Another point I wanted to bring up here is something called the separation fallacy. So when I put in a beam splitter and I put in these 2 detectors, is this an experiment so that I've measured this and I have just a photon traveling on one path or the other, or does it travel in superposition? Now, I'll let you think about that for a moment, but I am going to flash up the answer. It is a superposition because it can be reversed. If I put together a Mach-Zehnder interferometer with 2 mirrors and another beam splitter, I can get a situation where the light that comes in, all of it comes out this path to the bright detector if the path lengths are exactly the same on the sample path and the reference path. And that means that I just went through here and the experiment did absolutely nothing. It just took the photon and it continued on that horizontal path, just diverted a little bit by the mirrors. Okay, and this is actually very similar to what would happen in a 2-slit experiment. You can think of a nice analogy of this with 2-slit experiments as well. Okay, now let me ask you a question. How would you respond to this question if you were asked this question by a student? What variables can be measured in physics? And by physics, we should really focus quantum physics or in quantum mechanics. Is it only the position of a particle that is always measured and the rest of the variables are inferred from it? Now, this is a question that was actually posted on Quora, and I'm going to take one of the common answers that was given to this person who posted it. It was the following, which is the quantum mechanics party line. Dynamic variables including position, momentum, phase, spin, orientation, and polarization can be measured independently, but non-commuting operators cannot be measured at the same time. And you're probably sitting there nodding your head saying, yes, this is the way, this is a good answer. This is what you should be saying. I like to call this, if it is a Hermitian operator, it can be measured, but it must respect unitarity, must respect uncertainty. But isn't the detector located at some position when I do the measurement? Isn't it always de facto measuring position along with whatever else it measures? Let's take a close look at a really important measurement called a time of flight measurement. This is used a lot in cold atom physics. An event is used to start a clock. The particle travels through free space to a detector where it's detected. We divide the distance traveled by the time to compute the speed. And from the speed, we get the momentum, since we know the mass of the particle. Now, at the instant of measurement, we know the position and the momentum of the particle at the same time. Of course, we don't know what happens to this particle, because typically in the time of flight experiment, the particle gets destroyed. But what's going on with uncertainty? We're measuring the position and momentum at exactly the same time. And in fact, if you don't like it for time of flight, just look at a particle scintillator. That's a detector that's located at a position and measures the energy. So that's measuring position and energy at the same time. Or if you like, if you've oriented it where you can tell the angle of the path that the particle comes in, you can infer, again, position and momentum from your detector. This does not violate uncertainty. It's simply not true to say that you cannot measure position and momentum at the same time. You can. Please do not tell your students that you cannot do this. Uncertainty only enters when you look at many measurements, and then the uncertainty that you'll get, because you get different times in the time of flight, the uncertainty you'll get is the uncertainty of the initial distribution plus whatever spreading you get, because it's spreading as a free packet, free wave packet as it's traveling through free space to your detector. What's the point I'm trying to make? Quantum measurement is difficult and subtle. We should always describe precisely how it's done and never say it can just be done. We should never talk about an experiment without describing how the experiment is performed. Let's take a look at a beautiful delayed choice experiment, the demonstration by Paul Nord of Valparaiso, who is an absolute expert in demonstrations. He has a YouTube channel that is really beautiful. What he's doing here is he's setting up a diffraction experiment where he has a clear piece of glass with a wire, and he's diffracting the laser light about the wire, and you can see this beautiful diffraction pattern coming from the diffracted light about the wire. Now what he's going to do is he's going to take a different source, and he's going to put two cross polarizers, one vertical, one horizontal, on each side of the wire. And you can see here he's showing you the two different polarizers on the two different sides. Now he's going to put this in. He's going to go to the screen with his polarizer, and it's going to allow him to do a delayed choice measurement to select which side of the screen he's seeing the features from. So initially, he's going to be showing us the results from either side. And you can see there's no interference there because I have which way information from the polarization. Now he's picking the light from just one side by putting in either a vertical or a horizontal polarizer. But if he puts it in at 45 degrees, which he's going to do in just a moment, you're going to see the interference comes back. And this is such a beautiful demonstration. Look at that. Look at how beautiful that is. The interference comes back. This is a nice delayed choice experiment. It has nothing to do with retro causality or going backwards in time or anything crazy like that. It just follows very simply from a quantum mechanical measurement where you introduce and use the ideas of tagging. This is where tagging comes important in looking at delayed choice experiments. Okay, how about interaction-free experiments? These are beautiful experiments, and you've been teaching about a simple interaction-free experiment all the time, but no one mentioned it in the quantum mechanics textbook. So I'll pause for a second and see whether or not you can think of what is the simple interaction-free experiment that is one of the founding experiments of quantum mechanics. Indeed, it's the Millikan oil drop experiment. Now, you might notice that's not Millikan that I've given there. It's actually Harvey Fletcher. And the reason is Harvey Fletcher is actually the guy who came up with the idea for the experiment. He was the graduate student. There's a beautiful Physics Today article about the Millikan experiment and Fletcher's role. And when you read it, you realize that it really should have been called Fletcher's experiment. But how does this work? We do a measurement by floating a ball of oil that has extra electron charges on it, and we balance it with a voltage. Where's the entanglement? Where's the collapse? None of that is happening. It's a beautiful interaction-free measurement. We're inferring the charge of the electron by applying a voltage that makes an oil drop float. Absolutely beautiful experiment. Interaction-free experiment, really nice one. Another question you might be faced with asking is the wave function real? So let's look at this experiment that we were talking about before where I separate on a 50-50 beam splitter and I have two detectors. Does it travel in superposition until detected as the Copenhagen interpretation would tell you? Or does it actually travel on a definite path? Can we tell? So if you looked at the quantum histories, consistent histories approach, that would tell you it's traveling on a definite path. And if you think about a two-slit experiment with detectors, you would also say it goes through one slit or the other. We're not bothered by that. But somehow when we do it in this geometry, because the detectors can be far separated from the beam splitter, we get bothered by saying that I can tell which path the particle takes, but I can tell which path it takes. And in fact, there's no way to tell in a measurement how you could tell that you should interpret this in a Copenhagen way versus, say, a consistent history way. Because if there was, we'd do that experiment and we would tell which one was right. So both are valid. The one thing you cannot say is what is called separation fallacy, which tells us that if I set the photon through here and then I remove the detectors, then it went from going on one path only and goes back to being in a superposition. That would be a false thing to say. The consistent history changes if I have the detectors there versus if I don't have the detectors there. And that's a very important point to keep in mind. So I want to encourage you to teach about real experiments when we teach quantum mechanics. We have a great opportunity to improve quantum mechanics instruction with a focus on sensing, and I hope you'll come join with me in trying to make the experience better for students and making them prepared for a quantum-enabled workforce. And I'd like to then end by thanking the National Science Foundation, the Center for New Design of Learning and New Learning at Georgetown University, edX, and the McDevitt's, who donated money for the endowed chair that I have. And for resources, I'm going to just list the 3 different resources that I have where you can find information. I have a website that I have all of my pedagogy-related material there. And I'm focusing on 2 edX courses, one which is a quantum mechanics course for undergraduates that shows you in more detail how you can do all of this, and another one is a quantum mechanics course for non-scientists, which focuses on those 5 critical ideas about superposition, entanglement, tagging, complementarity, and measurement. And with that, I'm going to thank you very much, and hopefully I'll be live and able to take questions, but if this is hybrid, please feel free to post any questions that you have. Thank you very much.